So hello teacher, my name is Dũng, and today on behalf of my group, I'd like to introduce you to our group project. But first, let's take a little look at our team member. So our team consists of 5 members, myself, Nguyễn Dũng, and for my friends, Nguyễn Thanh Bình, Nguyễn Thiên Lộc, Đoàn Thế Anh, and Thái Quang Dự. And here's our table contribution. Personally, I will brainstorm the idea, design the PowerPoint, and make presentation. Quang Dự and Thiên Lộc, we do the research on problem 1. Thanh Bình, Thế Anh, we do research on problem 2. So, okay, let's jump right in. So our project has 2 main topics. First, we talk about the method of Lagrange multipliers and solve some of the problem. And second, we will dig deeper into real application of calculus 2. So what exactly is the method of Lagrange multiplier? So it's the strategy for finding the local maxima and minima of a function subject to equality constraints. It's named after the mathematician Joseph Louis Lagrange. The basic idea to convert the constraint problem into a form so that the derivative test of an unconstrained problem can still be applied. So here, answer to the question 1A, you ask what we need to focus on this point to solve the problem for finding the maximum and minimum value of f on the curve gamma. So the critical point x0 and y0 is where the contour line of xy and gxy are tangled. So it's the same point where the gradient vector fxy and gxy are parallel to the side and proportional to each other. Connect to question 1B. For the number lambda mentioned above, it's possible that lambda equals to 0. So yes, when the constraint is not binding, in other words, it don't have co-area in a circle ellipse, or when an unconditional stationary point of xy happen to lie on surface defined by the constraint. But last but not least, question 1C, can the Lagrange method be used to find the maximum minimum value on the function fxy equal x squared plus y squared for xy on the curve x to the power 4 plus y to the power 4 minus x equal to 1. So here's our answer. So the maximum and minimum of fxy and gxy are the derivative of f following x equal to 2x and the derivative of f following y equal to y and etc. So got gx equal to 4x cubed minus 1 and gy for e cubed y cubed. So we got the gradient of f equal to lambda multiplied by the gradient of the function g. So got 3 of the equation below. And if y is equal to 0, then x to the power 4 minus x minus 1 equal to 0 and 2. We have 2 values of x is 1.22 and 0 minus 0.72. And so in these two function, we get to y squared equal to x squared minus 1 to over 4x. And from 1 to we get 2x to power 4 minus 1.5 x minus 1 plus 1 over 16x square equals 0. When we got if x equal to 1.06, then is a that and minus 0.696. If x equal to 0.22, then y equal to plus and minus 1.05 to get the m1 point 1.22 and 0 equal 1.4884. M2 the point M2 is minus 0.72 and 0 equal to 0.5184, and the same for M3 here and M4. So the maximum is M3, the point M3 which is 1.06 and 0.96, and M5 1.06 and minus 0.96, which is the 2.0261, and the minimum is M2, the point M2 minus 0.72 and 0 equal to 0.5184. And next up, we will talk about the real application of calculus 2. We want to use calculus 2 to model epidemics. So an interesting real-life problem that requires the use of concepts to the calculus 2 in modeling the spread of infectious disease using different equations. For instance, consider a problem modeling the spread of COVID-19 in the population. Let ST, IT, and RT denote the number of susceptible, infected, and recovered individuals, respectively at time t. So assume the rate at which the susceptible individual become infected is proportional to the product of number of susceptible and infected individual. So the rate at which the infected individual will recover is proportional to number of infected individual. Then we can model spread of disease using the following system, the different differential equation. We got delta S over delta T equal to minus KSI, and delta I over delta T equal to KSI minus RL, and dr and delta R over delta T equal to RL, where K and R are positive constant that represent the transmission rate and recovery rate of the disease, respectively. So solving the system of differential equation using calculus 2, we can determine how the number of susceptible, infected, and recovered individuals change over time and make prediction about the future course of the disease. One last example is the SRI model. We divide the population into 3 categories: susceptible as, infected are, and recover are. The model assumes that the total population and remain constant, and the individual move between the category according to the following set of different equation. So delta S over delta T will equal to minus beta Si over N, and delta I over delta T will equal to beta Si over N minus gamma I, and dr over dt will equal to gamma I, and here B is the transmission rate, and gamma is the recovery rate. The term beta Si over N represent the rate at which the susceptible individual become infected, and gamma I represent the rate at which infected individual recover. The term minus beta Si over N in the equation for delta S over delta T represent the rate at which susceptible individual are become infected, while the term gamma I in the equation for delta I over delta T represent the rate at which infected individuals are recovering and become immune. Finally, the equation for dr over dt represents the rate at which the individual are moving from the infected category to the recovered category. So to illustrate the model, let's assume that we have population of 10,000 and equal 10,000, and the transmission rate beta is 0.3 and recovery is 0.1. We can stimulate the spread of an infected disease over time using a numerical method, just the Euclid method. So starting with an initial condition of 100 infected individual and the rest is susceptible, we can update the differential equation at each time to step to obtain the following result in the table below. You can check it out. As you can see, that the model predicts that the disease will spread rapidly at first, with the number of infected individuals increasing exponentially. However, as more and more people become immune to disease, the rate of spread begins to slow down until eventually the disease dies out. This because the pool of susceptible individuals becomes smaller and smaller, making it less likely that the infected person will come into contact with someone who can still catch the disease. Of course, this simplified model doesn't take into account many real-world problems, but such as variation in transmission and recovery rate, the effect of the vaccination, or the impact of the public health intervention. However, it provides a useful starting point for understanding the dynamic of infected disease and how they spread to a population. Calculus 2 concepts that like differential equations are crucial in modeling various real-life phenomena in population dynamic, fluid flow, heat transfer, and electronic circuits. Solving the system with differential equation using technique learned from calculus 2, we can determine how number of susceptible, infected, and recovered individual change over time and make prediction about the future course of the disease. We can also use this model to study the effect of different control measures, such as vaccination, social distancing, quarantine on the threat of disease, and make informed decisions about public health policy. So here's some more example of an SRI model of COVID-19. In this figure 1 is the epidemic development of COVID-19 in Hunan, China, Italy, the picture A and B, and the daily news COVID case in Hunan, China, Italy, C and D, epidemic distribution of COVID in Hunan, China, Italy. And we got the SRI model simulation for COVID-19 epidemic state of India from the 7th of May 2020. And we got some more examples of which n over a million s will equal to n minus 1, I equal to 1, r equals 0, beta equal to 0.5, and gamma equal to 0.1. So that is the end of our presentation. Thank you very much for listening and have a good day.